So now we know what law of cosines is, but why does it work? Let's do a proof for law of cosines. Let's show why it works. Yeah. If we want to figure out how law of cosines works, we've set up our typical triangle A, B, and C with opposite sides labeled as side A, side B, and side C, just like our law of cosines uses. If we want to set up this proof, the first thing we're going to do is drop an altitude. So we drop this altitude C, and a couple of things happen. First of all, we have this length, that is the distance from angle C's vertex to the base. Okay? It also breaks side length C up into two parts, and let's just for now call them Y and Z. The first step in our proof is going to be finding new expressions for X, Y, and Z that only use A, B, and C to represent them. Well, that shouldn't be too difficult because if you'll notice, we have two right triangles to work with now. So blowing up one of those right triangles, let's see if we can find new expressions for X and Y. Okay. Let's do it in terms of angle A. We could do it in terms of angle C instead if we wanted to, but let's just pick A. If we want to figure out what side X is equal to, we would use the sine of angle A. And sine of angle A would equal X divided by side length B. Well, if we are trying to figure out what X is equal to, we would multiply both sides of this equation by B, and we would come to the conclusion that B times the sine of angle A is equal to X. So we could rewrite this as B times the sine of angle A. And that's going to be better than X because it takes one of the variables out of the problem. We now have this side length in terms of the other variables. Let's do the same thing for side length Y down here. Okay. To start off, we've got, instead of sine of A, cosine of angle A is equal Y over B. Just like we did last time, multiply both sides by B. And we're going to find out that Y is equal to B times cosine of A. So this smaller segment of side length C in our triangle can be represented as B times cosine of angle A. Okay. So now that we've done that, let's move forward and let's find out what this side length would equal. Now there's a couple of ways we could go about that. We could draw the triangle that has hypotenuse of A, which is a right triangle. Okay? And we could do something that involves sine, cosine, or tangent of angle B. But what's going to be better than that, actually, is keeping things in terms of angle A. And we can keep things in terms of angle A if we remember that this entire side length is C. If this entire side length is C, and this side length we already have an expression for, B times the cosine of A, then I can figure out the part that's left over simply by subtracting. C minus the part that's on the left. C minus B times cosine A. So this whole length minus the smaller portion. So that's where we are now. The next step of the proof is a little bit tricky, and you could pause here and spend some time thinking about how you might approach this to set up some law of cosines. But if you played around with it long enough, you might eventually recognize that if you take this triangle right here and then apply that most famous of theorems that involves right triangles to it, the Pythagorean theorem, that with a little bit of algebraic manipulation, which we're going to do in just a second, you will be left with what we call and what we use as the law of cosines. Okay, so let's remind ourselves that the Pythagorean theorem is one leg squared plus the other leg squared will always equal the hypotenuse squared. Okay. So let's plug our values in. Okay. For the first leg, which we are going to square, we're going to plug in our value B times sine of angle A. we're going to add to that the other leg squared, which in this case is c minus b times cosine of angle A. And then that should equal side length A squared. Oh, I left off my squared here. So this is a Pythagorean theorem using our green triangle here. Well, we need to simplify this, so let's start with b times sine of A squared. Well, if I'm multiplying this b times sine of A times b times sine of A, well, b times b is b squared, and sine of A times sine of A is sine of A squared. Plus, this is a little bit more difficult to multiply, but it's not that hard if we remember that this is something like x minus 2 squared. And when we did x minus 2 squared, we learned that we have to do x minus 2 times x minus 2. And then use our rules for multiplying binomials or polynomials. Okay. Well, that means we're going to do c minus b cosine of A times c minus b cosine of A. To multiply these using our rules from algebra, we have to multiply each part in the first by each part in the second. So c times c is c squared. C times b cosine A is negative b times c times cosine of A. Negative b cosine A times c is again negative b c times cosine of A. And negative b cosine A times negative b cosine A is positive. Negative times a negative is a positive. B squared cosine of A squared. You may or may not recognize that these two middle terms are like terms. They're both b times c times cosine of A. So we can combine like terms and simplify this to c squared minus 2bc cosine of A plus b squared cosine of A squared. So there are parts of this that you might start to recognize from the law of cosines. So let's add this in to our Pythagorean theorem problem up here. Minus 2bc cosine of A plus b squared times cosine of A squared. That should all equal A squared. Okay, now at this point we need to do a little bit of simplifying, and it may or may not come natural to you where we should go next. But as I look at this, what I notice is I've got these two things here that both look quite similar to each other. They both have a b squared and then times either sine or cosine of angle A squared. So I'm going to come bring them together. B squared times sine of angle A squared plus b squared times cosine of angle A squared. All I've done is rearrange things using commutative or associative properties. Plus c squared minus 2bc times cosine of angle A should equal A squared. As I look at this, I will remember how to factor polynomials by something called the GCF, the greatest common factor. Both of these terms have a b squared in them. And so that means I could factor out this b squared and rewrite it as a distributive property problem. And that's going to give me b squared times sine of A squared plus cosine of A squared plus c squared minus 2bc times cosine of A equals A squared. And here's the point in the proof where I've got to jump a little bit ahead as far as your mathematical knowledge goes. In a couple of years, you'll take a trig class or pre-calculus class, and one of the things you're going to learn about is something called trig identities. Trig identities are the theorems of trigonometry. And in pre-calculus class, you're going to learn some of these trig identities, and you're going to do proofs that involve trigonometry. with them. Sines, cosines, tangents, other things you're going to learn, cotangents, cosecants, secants. Well, this, inside this parentheses, is one of the most famous, if not the most famous, of all trig identities. And this trig identity tells us that if you take the sine of an angle and then square that, and then you take the cosine of an angle, the same angle, and square that, when you add these two things together, you will every single time get 1. Every single time. Sine squared of an angle plus cosine squared of an angle will always equal 1. Okay? And just so that you don't have to believe me and take my word for it, let's see what Wolfram Alpha has to say on the situation. So, what we are claiming is that the sine of any angle squared plus the cosine of any angle squared should equal 1. So, let's see what Wolfram Alpha tells us. We put that in. Sine of 32 squared plus cosine 32 squared, we in fact get 1. If we don't believe this after just one test case, put in a different angle measurement, remembering always making them the same. Sine of 79 squared plus cosine 79 squared is in fact 1. Okay. And because Wolfram Alpha is a website of math magic, we could do it just with x, in case you don't believe me still, and we find out that no matter what value we put in for sine squared and cosine squared, we do in fact always get, as a result, 1. I'll prove this in another video just to demonstrate why this trig identity is true, so that you don't have to take Wolfram Alpha's word for it. But for now, what we can do is say, hey, this value is 1. And so when I multiply b squared times this sine squared plus cosine squared, I'm going to get b squared. And so we are now going to come to what we have learned to be the form of law of cosines, b squared times 1, which is b squared, plus c squared minus 2bc times the cosine of angle A is equal to a squared. Okay. Of course, this is not the only form that law of cosines fits into, but you can see how it would be easy to rearrange these letters or to draw a different altitude and do the same proof to get all 3 versions of law of cosines. And we've proven law of cosines. We now know that it must work for any triangle ABC.